Hello everyone, welcome to the special lecture on chemical equilibrium. We are continuing with the last lecture to study more about chemical equilibrium and going through a little bit more concepts and some calculations. Let us do a recap on what we did the last time. We were asked to write equilibrium constant expressions for the following four reactions. The first equilibrium is pretty straightforward. It's very easy to write the Kc expression because all the reactants are in equal states. So basically we just have to do a division. For the numerator, we have to consider the concentrations of the products, the concentration of the products, raise them to the appropriate power and multiply them together. And for the denominator, we have to multiply the concentration of the reactants and raise them to the appropriate power. For the second equilibrium, you have realized that we have the presence of water as a liquid, as a solvent, and BiClO as a solid product from the reaction. Now you know that in Kc we do not consider solid and liquid when we are writing the expression. So in the end, the Kc expression ends up to be just consisting of the concentration of HCl over here raised to the power of 2, and the concentration of BiCl3 raised to the power of 1. And all these are indicated by the molar ratio. Third and fourth example, we were told to write the equilibrium constant expression in terms of Kp. So Kp, we are writing them in terms of partial pressure. So partial pressure, we do not consider any solid or liquid in the expression. So over here in the third example over here, we have iron over here as solid and Fe3O4 here as a solid. So we do not take them into account when we write the equilibrium constant expression in terms of Kp. So if after considering all of this, the Kp expression would be the partial pressure of H2 raised to the power of 4 over the partial pressure of water vapor raised to the power of 4. In the fourth example, we have the presence of liquid bromine over here. So like the previous example, we do not consider any other thing other than gases in the reaction. So the Kp expression becomes the partial pressure of hydrogen bromide, okay, raised to the power of 2 over the partial pressure of hydrogen raised to the power of 1. That's what we did the last time. So you may be asking, what is the significance of Kc? What is the meaning of a big Kc and the meaning of a small Kc? Okay, a big Kc versus a small Kc. Now if you can recall, Kc measures the extent to which reactants are converted to products. And this is only applicable for reversible system in a dynamic equilibrium. Let us look at this chemical reaction. You can very easily write the Kc expression. So if the Kc is small, okay, I will indicate it over here as a downward arrow. How do you get a small Kc? You can get a small Kc if the fraction on the other side is like this. The denominator is very big and the numerator is pretty small. And this means that the conversion of the reactants to products is low. In other words, in the equilibrium mixture, okay, the composition is rich in the reactants A and B. If we have a large Kc, how can it happen? It can happen when the denominator is small and the numerator is big. So in this case, the conversion of the reactants to the product is high. And the equilibrium mixture is rich in the products C and D. Now over here we have a table summarizing the significance of Kc. What happens if the value of Kc is small? What does it tell us about the composition of the equilibrium system, and what does it how is it being represented in the concentration time graph? So let us consider the two values, one big and the other one is small. So if the value of Kc is small, you would know that the composition of the equilibrium system would consist mostly of reactants and very little products are being formed. So if you look at this concentration time graph, the concentration of the reactant would drop because it's being converted into the product, but it doesn't dip so much. Okay, it just dip a little, and it reaches equilibrium already. Okay, similarly for the product, we get a bit of the product and then it goes on to be in the equilibrium concentration after a while. Okay, not much conversion over here, but if you consider a large Kc, a reaction with a large Kc, this would mean the composition of the equilibrium mixture consists of lots of product and the reaction is almost complete. In fact, for a reaction that goes in one way, a one-way reaction, the Kc can be said to be infinity. And if you look at the graph over here, the concentration time graph, the reactant, there will be a huge dip, okay, and then there will be a huge increase in the concentration of the product because the reaction goes almost to completion. Of course, since we are dealing with equilibrium system, after a while, the amount of product and reactant reaches a constant. And an important point regarding Kc is that the equilibrium constant indicates to us the extent of the reaction, but it does not give us any information on the rate of the reaction. It tells us how far, but not how fast. If we are going to consider an analogy, this analogy I think would be very appropriate. Now imagine two turtles racing from the start line to the finish line. Okay, and the two turtles are walking in a straight line towards the finish line. Now, if you can indicate to me the progress of the competition between the two turtles by a number known as Kc. Now Kc will tell me how far the turtle is away from the start line or how near it is to the finish line, but it cannot tell me how fast the turtle is traveling. Now let me say that again. If you can represent the progress of the race using the number known as Kc, the Kc of the competition would tell me how far are the turtles away from the start line or how near the turtle is near the finish line, but it cannot tell me how fast the turtles are traveling. Okay, so the same goes for a chemical reaction. If you apply Kc to a chemical equilibrium, it can only tell me how much the reaction has progressed from the reactants to the products, but it cannot tell me how fast it is going to take place. Now, a reaction can be very complete. Okay, that means that the Kc is very big. Okay, but it can take 1,000 years to complete. So the rate of the reaction can be very slow. Now, similarly, if we have a reaction, the reaction can be stuck mainly as the reactants, and it doesn't go to completion very much. It gives us very little products. So Kc in this case will be very small, but this reaction can take place maybe in a second. Okay, and Kc cannot tell us the reaction whether it will take 1,000 years or it will take a second.